Assalamu alaikum dear students. I welcome you to 26th lecture of probability and stochastic processes. In previous few lectures we have been working with transformation of random variables, in which there was an underlying experiment which generated an unpredictable value, and that value represented the underlying random variable or the original directly observed random variable. But we transformed the values generated by the random experiment to other values because these other values of more interest to us, and then we tried to analyze the behavior of these transformed values. The collection of these transformed values was representing a derived random variable. So we were more interested in the values of derived random variable than the original underlying random variable. And while analyzing the behavior of this derived random variable, while trying to answer the questions related to the behavior of the derived random variable, we needed its probability density function. And that probability density function was obtained from two pieces of information. One, the probability density function of the underlying random variable, and the transformation which took the value of the original random variable and gave us the output, which was the value of the derived random variable. For example, if there was an underlying random variable x and we knew the PDF of x, then we needed that PDF and a function g which was giving us values of y. Y is equal to g of x. So this function g took values of x as input and gave y as output. So y was our derived random variables, and values of y were the collection of values that we wanted to analyze. So initially, a few lectures ago, we were working with transformation of a scalar valued random variable, where the underlying random variable was a single random variable x, and transformed random variable was also a scalar valued random variable y, and the function which related the values of x and y was a function from R to R, y is equal to g of x. Then we moved on and started working with a pair of random variables, say x and y. So these two underlying random variables x and y gave us a PDF which was defined over a portion or whole of xy plane. And from this joint PDF, we were able to answer questions related to the joint behavior of two random variables x and y. And for that, we needed that joint PDF. But sometimes we were interested in a derived random variable, scalar valued, that assumed its values based on the values assumed by pair of underlying random variables. Suppose that derived random variable is z or z, then the values of z depend on the values of x and values of y, and all these three quantities are related by a function, say g. Now g is a function which takes two parameters, values of x and y, and give us one parameter, value of z. So this function is from R2 or R square, the plane, to R1 or single line. So it takes two values and gives us one value. So when we were working with a pair of random variables, we initially defined a single scalar valued random variable and analyzed the behavior of this single scalar valued random variable, which indirectly referred to the behavior of the two underlying random variables. To analyze the behavior of z, which was function of x and y, we wanted the PDF of z. This PDF of z was defined on real line, and we obtained that again from two pieces of information. One was the joint PDF of x and y, which was defined over plane. So it was a function which was R2 to R. The other piece of information that we used was the function g, which took two parameters, two inputs, and gave us one output. So that function g, which was z is equal to g of x and y, was also a function from R square to R. So we used two functions, one joint PDF and one the transforming function, both being R2 to R, and got a new PDF, a function which was from R to R. So when we were working with that, there was a lot of loss of information. Instead of working with two random variables defined over whole plane, we combined their values, got a single scalar random variable which was defined on a line with its PDF, which was a scalar valued function defined over R. And in previous two lectures, we extended this treatment to a pair of derived random variables which were defined over a pair of underlying random variables. In this case, we had two underlying random variables x and y, and their joint PDF was known, the PDF of x and y, which was again defined over a plane xy, and it was a function from R2 to R. From this known joint PDF of two underlying random variables x and y, we defined two new derived random variables u and v. The value of u is obtained from values of x and y through a function, say g, which is defined as u being equal to g of x and y. Similarly, the values of v are obtained using another function h. So h takes values of x and y and give out values of v. When we have a pair of derived random variables defined over a pair of underlying random variables, we do not make any assumption about mutual independence of u and v, and find their joint PDF first, from which we can find the marginal densities, and from these marginal densities we can establish if the two random variables u and v were independent or not. In all these cases, we wanted to find the PDF of the derived random variable from the PDF of underlying random variable or random variables and the transforming functions. For the case of scalar random variable getting transformed to a new scalar random variable, that is y equal to g of x, we followed a path which required us to find the CDF of the derived random variable first, and from this CDF we were able to find the PDF of derived random variable by taking the derivative of the CDF. Similarly, for the case of a scalar valued random variable being defined on a pair of underlying random variables through the joint probability of the pair of underlying random variables, we followed the same path. The path where we have to find the CDF of derived random variable first, and from that CDF we get the PDF by taking the differentiation. When we were working with a pair of derived random variables defined over a pair of underlying random variables, we took two paths to get to the joint PDF of pair of derived random variables. The first was the old path of finding the joint CDF first, and from that joint CDF we found the joint PDF by taking partial derivatives with respect to the two parameters of joint CDF. The other path was a direct path where we worked with the joint PDF of pair of underlying random variables, and from this joint PDF we directly reached to joint PDF of the derived random variables using the transforming functions g and h and their inverse transforming functions phi and psi. This path is slightly difficult to understand and it's not easy to follow. So I have decided to revisit this direct path where we reach the PDF of derived random variable directly from the PDF of underlying random variable using the characteristics of transformating functions g, h and inverse transformating functions like phi and psi. By revisiting this technique of directly reaching the PDF of derived random variable and applying this technique to simpler cases first, I hope to give you a solid footing and ability to understand this technique thoroughly and be able to apply this technique to simple as well as complex cases of transformation of random variables. Another advantage of revisiting this technique and applying it to simpler cases is that I hope you will be able to apply this technique to those cases where the transforming function is not invertible. So far we have restricted ourselves to those functions which were simple, invertible, so that a small event in the sample space of transformed random variable corresponded to a small event, a single small event in the sample space of underlying random variable. Today we are going to remove this restriction and work with those transforming functions which are non-invertible, which are many to one. So let's have a look at this technique as it is applied to a simple case of a scalar random variable getting transformed to another scalar random variable. That is, we are going to work with directly reaching the PDF of a derived random variable y from the PDF of an underlying random variable x when x and y are related to each other through a function g which gives us y is equal to g of x. Let's have a look at a simple case of transformation of random variable x to random variable y. With such a transformation, there are three functions that play their role, and these three functions are shown on this screen. The first function is the PDF of x. It is defined for values of x, and its value represents the relative likelihood of different values that random variable x can attain. Here, a general shape of this PDF is drawn, and it is assumed that it is defined for the whole real line. The second function is the transforming function g. G takes values of x and gives you values of y. This is the PDF of y, which is also defined over the whole line, and here is a general shape of this PDF. Please note that this PDF is not known yet, and we need to find this PDF. And to reach this PDF, we need a function g which relates the values of x to values of y. If there is a function g which relates values of x to values of y, there is a corresponding inverse function, say h, which is g inverse, in such a way that composition of two functions g and h is a unity function which maps the points to themselves. Here on your plasma screen, I have drawn this inverse function, and I have assumed that for this simple case, this function g is invertible so h is also a function. So this plot is the plot of function h. It takes values of y as input and give values of x as output. G, the original transforming function, takes values of x and give values of y. So this plot is for G inverse or h. Now the problem is that you want to find the PDF of derived random variable y. To find that, pick a point y. This point is shown here. This is a general point. You can pick it here, 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 anywhere where the random variable y assume its value. So when you have picked a point y here, form a small event, an event with small probability by picking another point near this point y, and the distance between this point and this point is just dy. So if this point is y, this point is y plus dy, because we have picked the other point to the right of this point y. Now this range of values of y defines an event, and probability of this event is equal to integration of this PDF of y over this interval. So this blue region represents the probability of that event where random variable y takes on values from y to y plus dy. Assuming that y and y plus dy are very close to each other, that is, this dy is much smaller than 1, then we can assume that this PDF of y remains flat during this interval dy. If that's the case, then this blue region is rectangular in shape, and the area of this rectangle will be the height multiplied by the width of the interval. The height is the value of this PDF at this point y, and the width is dy. So probability of this event that random variable y takes on values from y to y plus dy is equal to value of this unknown PDF of y at point y multiplied by dy. So this event on sample space of y has a corresponding event on sample space of x. The question is, how do we reach from this event to that event? And if we can find a way to reach to that event, we can find the probability of that event and equate the two probabilities, which in turn will allow us to equate or find the relationship between PDF of y and PDF of x. This relationship is defined through this function h, which is the inverse transformation from y to x. The inputs are values of y and the outputs are values of x. So let's have a look at this inverse function and see how it helps us give an interval on x, PDF of x, from this interval on PDF of y. If we take these 2 points y and y plus dy and put them here, then this inverse function gives us 2 points. For y, we have inverse image of y, which is x2. And for point y plus dy, we have its inverse image, which is x2 dash. Please note that x2 dash is larger than x2 because at this point, slope of this inverse function is positive. So as we move from y to y plus dy, the inverse image moves from x2 to x2 dash. So these are the inverse images which are shown here, x2, and to the right of that x2 dash, because x2 dash is larger than x2. So these 2 points are inverse images of these 2 points. So this interval, which spans values of y from y to y plus dy, is equivalent to this interval which spans values of x from x2 to x2 dash. And it's easy to find the probability of this red region by integrating this PDF of x from x2 to x2 dash. But we actually do not have to integrate this, because we can again see from the slope of this inverse function that if y and y plus dy, the 2 points are very close, so are the 2 points on x-axis, because then this x2 and x2 dash should also be close. And we can again assume that the PDF of x does not change much when we move from x2 to x2 dash. So we can assume that PDF of x remains flat, and the probability of that interval in terms of random variable x will be the difference between x2 and x2 dash, or subtraction of x2 dash minus x2, that interval, multiplied by the value of PDF of x at point x2. But the question is, how do you find the location of this point x2 dash? x2 is inverse image of y. But what about x2 dash? How far away from x2 it is? The hint is in this inverse function. If you look at these 4 points y and x2, which forms this point, and y plus dy and x2 dash, which is the coordinate of this point, you can see that this inverse function changes from this point to this, but we can assume that this is straight line from here to here. Once again, we are referring to the Taylor series of this function, the inverse mapping representation of this Taylor series, and then discarding all those terms which have second, third or higher powers of this small interval dy. Or in other words, graphically, we are assuming that this is a straight line. When this is a straight line and you know this interval, you know the length of this interval, if you know the slope of this straight line, and slope of this straight line is nothing but the derivative of this inverse mapping at this point y. So if this inverse mapping is h, then dh over dy is the derivative, which can be also said to be h dash. So h dash is derivative of inverse function h with respect to y, and h dash y is the value of that derivative here. If you know the value of that derivative, then it's easy to see that this interval divided by this interval is equal to that derivative. Hence, this interval is equal to value of the derivative multiplied by this interval, which is dy. Hence, the interval this x2 to x2 dash is nothing but the value of the derivative of h at y multiplied by dy. So if we know this interval, we know the value of the PDF at point x2, we can find the probability of this event on this sample space of x, which comes out to be value of PDF of x at point x2 multiplied by dy multiplied by the value of the derivative of h at this point y, where we are trying to find the PDF of y. If you equate these things, it's easy to see that the value of PDF of y at a general point y is equal to value of PDF of x at inverse image of that point y multiplied by the value of derivative of inverse mapping h at that general point y. If you sit down and draw this diagram yourself and work these things out, you will get insight into this direct methodology where you get to the PDF of scalar valued derived random variable y directly from the PDF of underlying scalar valued random variable x. Let's have a look at another variation of this simple case of transforming a scalar valued random variable to another scalar valued random variable. In this case, the only difference is that this inverse function h at this point y has a negative value of derivative. With this change, the treatment of this case becomes slightly different, but we will analyze this quickly to find out how this case can also be handled very easily. So once again, there are three quantities which are playing their role: the joint PDF of x known, the inverse mapping h which relates to the original mapping g in such a way that if g takes point x and gives a point y, this mapping h takes a point y as input and gives a point x as output in such a way that composition of g and this h is a unity transformation which gives the same point back. We want to find the PDF of derived random variable y at a general point y, and we take another point y plus dy from this interval and assume that joint PDF is flat over this interval, and the value of this probability, the probability of this event, is the width of this interval multiplied by the unknown value of the PDF of y. This interval has a corresponding interval here in sample space of x. So if y gets mapped to x1 here, then y plus dy gets mapped to x1 dash. Please note that due to the negative slope of this inverse function, this y gets mapped to a point x1 which is higher compared to the inverse mapping of this point y plus dy which is lower. So x1 dash is to the left of x1. The width of this interval on x-axis can again be found by relating the width of the interval from y to y plus dy and the slope of the inverse function. This slope is again assumed to be of a straight line because of the Taylor series and rejection of all the higher powers of dy. By referring to that idea again, it's easy to see that interval from x1 dash to x1, this interval is equal to the width of this interval multiplied by the slope of this inverse mapping h. By equating the probabilities of two equivalent events, one shown in blue on random variable y and other shown in red for random variable x, we can find the relationship between PDF of x and PDF of y. It's easy to see that probability of this blue event is the value of this unknown PDF of y at point y multiplied by the width of this interval, and the probability of equivalent event which is shown in red is equal to width of this interval multiplied by the value of PDF of x at this point x1, which is inverse mapping of this point y. So this point y gets us a point x1, and this point x1 is here, and we assume that the value of PDF of x at point x1 and a neighboring point x1 dash is same. By equating the two probabilities, we can see that the probability on random variable y is PDF of y multiplied by dy, and probability of this equivalent event on random variable x is value of PDF of x on inverse mapping of this point y multiplied by dy multiplied by minus of the value of derivative of inverse mapping. This minus is due to the fact that this inverse mapping had a negative slope at point y, and when you take all these negative and positive quantities into account, you have to introduce another negative so that the interval on x-axis is from x1 dash to x1. So if the derivative of inverse mapping is positive, we use it as it is, but if it is negative, we introduce another negative. So in other words, we always use the absolute value of the derivative of inverse mapping. So general formula which relates the PDF of y and PDF of x, if x and y are related to each other through a mapping G, which uses y is equal to g of x, and an inverse mapping H, which is x is equal to h of y. If these are the kind of quantities which relate all these things, then the PDF of y at a certain point y is equal to the PDF of x at a point which is inverse map of this point y multiplied by the absolute value of derivative of the inverse mapping H at this point y. You don't have to fix this point y at a particular value. You can make it a parameter, change it over the whole real line, and as you change the location of this point y, you get a new value of PDF of y at that point. So by making this y as a parameter, you get the PDF of derived random variable y, which is equal to the PDF of the underlying random variable x, where x is replaced by the inverse image of y multiplied by the absolute value of derivative of inverse function h at the value of y, that is what you have chosen over the whole real line. So this is a general relationship between PDF of x and PDF of y when x and y are related to each other through two mappings G and H, which are invertible and simple. We can extend this discussion to include those mappings G which are not simple, which are not invertible. Then the analysis is slightly more difficult, but it's not very difficult, and once you have worked on these simple cases of invertible mappings G and H, you can easily extend these ideas to solve for those cases where G is a many to one and non-invertible mapping. When we are dealing with transformation of a scalar valued random variable x into a scalar valued random variable y through a mapping G which is not invertible, then there are three functions which play their role, and these three functions are shown on your screen. The first is the PDF of random variable x, the underlying random variable, and this is known. The other is the mapping G. Here I have shown mapping G, and in previous cases I was showing the inverse mapping H. So as you can see, this mapping G is a function. You can do the vertical line test and see that if you draw a vertical line, it crosses this graph of the function at one point, but if you draw a line like this, then it's possible for this line to cross at 2 points. So this function is many to one. This is the map of G, and for this point x1 as well as this point x2, the value, the height of the function is same. So the 2 points x1 and x2 give you a same value y. So this is 2 to 1 function. This function can be a quadratic or any other higher polynomial or some trigonometric function, but the point is this function g, whose map is shown here, is not invertible. It is 2 to 1. It could be many to 1, but here it is shown as 2 to 1. And the third quantity of interest is the PDF of derived random variable y, which is unknown. And the procedure to find this unknown PDF is same, that you pick a point y somewhere on the domain where random variable y assumes its values, and close to that point you pick another point y plus dy. So probability of this blue event defined in terms of random variable y is equal to the width of this interval, which is dy, multiplied by the height of this unknown PDF at point y, assuming that this PDF remains constant over this very narrow interval with width dy. Now this probability of blue event can be related to probability of some equivalent event defined in terms of random variable x. And how do you reach to that equivalent event? It is through this mapping G. So let's have a look at this mapping G, where x-axis is input and y-axis is output. So it takes values of x and gives you a value of y. So if you want to use this mapping G in inverse fashion, then you put value of y here and see what are the corresponding one or more values of x. In this case, there are two of them. So you first put value of y, draw a horizontal blue line and see where it cuts this mapping. It cuts the mapping at x1 and x2. So there are two solutions corresponding to y getting inversely mapped to x1 and x2, or in other words, the original mapping G takes points x1 and x2, and when mapping G is applied to x1 and x2, the result of both operations is equal to y. So this point y inverse map to point x1 and x2, and similarly this point y plus dy, which is shown here, gets inversely mapped to this point x1 dash and this point x2 dash. Assuming that this mapping is a straight line between this narrow interval with vertical width dy and horizontal width shown here and horizontal width shown here, you can see that when x is in this range, the mapping is in this range. Similarly, when x is in this range, the mapping is in this range. So if you want to find the inverse mapping of y being in this range, the answer consists of two parts. One is that x is in this range, the other is that x is in this range. So there are two events in random variable x which give you this event in random variable y. The first event in terms of random variable x, which gets mapped to this blue event on random variable y, is that random variable x assumes its values from x1 dash to x1. And the second event in terms of random variable x, which gets mapped to this blue event on random variable y, is that random variable x assumes its values from x2 to x2 dash. Let's see where these two events are in terms of random variable x and its PDF. So this is the first event where random variable x assumes its values from x1 dash to x1. This is the second event where random variable x assumes values from x2 to x2 dash. Both of these events get mapped to this blue event. So sum of probability of this event and probability of this event is equal to probability of this event. So how do you find probabilities of these two events? Assuming that if this is very narrow interval with width only dy, then these two are also narrow intervals on x-axis, and assuming that these are so narrow that values of PDF remain constant during these intervals, you can find the probability of this interval as the height of this PDF at point x1 multiplied by width of this interval plus the probability of this event, which is the height of PDF of x at this point x2 multiplied by the width of this interval. Please note that these two widths can be different. They don't have to be same, and these widths are related to this width and the slope of this mapping at the two solution points x1 and x2. As you can see, at x2 the slope of this mapping G is large, and at this point x1 the slope is small. Absolute number is small. Actually it is a negative number, but the absolute value of this slope is small. So this is a larger interval. So how do you relate the widths of these intervals on the PDF of x to the width of the interval on PDF of y? Once again, this relationship is established through this mapping G, because this mapping G maps that interval with width dy to two intervals from x1 dash to x1 and x2 to x2 dash, and the widths of these two intervals can be found by assuming that this mapping G is a straight line between those intervals. And once again we are relying on the expansion of this mapping G in terms of Taylor series and discarding of higher powers of dy. So assuming that this is a straight line here, the slope, which is the derivative of this mapping G, is equal to this width dy divided by this interval. So this interval is equal to this width divided by this slope. Similarly, width of this interval is equal to this width dy divided by the slope of this mapping at this point. When you combine all these quantities together, you have a relationship between unknown PDF of y and known PDF of x and the quantities which are derived from this mapping G. And the relationship is that the unknown PDF of y is equal to sum of some quantities, where each quantity is from the solution of this inverse mapping from this point y to points x1 and x2. So if there are two solutions in the inverse mapping, there will be two quantities in the expression for PDF of y. And if there are more than two solutions, then there will be more than two expressions. Well, each expression will be equal to the PDF of x, where x is replaced by the inverse mapping of y on that point x, multiplied by the absolute value of derivative of the inverse mapping at that point. And if you look carefully, this can also be shown as 1 over the absolute value of derivative of direct mapping. So the form of unknown PDF of y will be summation of f of x at xi, where xi is x1, x2, x3, corresponding to the solutions of inverse mapping, multiplied by 1 over absolute value of derivative of direct mapping G at the point where point y gets mapped through inverse solution. So if the mapping G is many to 1, then there are many events in random variable x which get mapped to a single event in random variable y, and PDF of y will have multiple components, and each component will come from those events which combinedly get mapped to event on Y. We can apply this principle to other cases of transformation of random variables. For example, in previous lectures, we were discussing a pair of derived random variables u and v, which were defined in terms of a pair of underlying random variables x and y. And we assumed that all these mappings g, h, phi and psi were invertible. So one region in uv plane gets mapped to one region in xy plane, and we were able to relate these regions, find their areas through Jacobian of the transformation, and relate the joint PDF of u and v with joint PDF of x and y. But suppose that these mappings g of x comma y, which gives us u, and h of x comma y, which gives us v, are not invertible. They are many to one, and there are many examples where these mappings can be many to one. For example, if g of x comma y is x square plus y square, then there will be 4 pairs of points x comma y which will give you a single value u. Similarly, if the mapping h was h of x comma y is equal to x into y, then there will be 2 pairs of points x comma y which will give you a same value of v. For these kinds of many to one mappings, we can still find the joint PDF of u and v in terms of joint PDF of x and y and these mappings. And the clue is what we just discussed in the case of non-invertible mappings as applicable to transformation of scalar valued random variables to scalar valued random variables. And in the case of pair of derived random variables defined on a pair of underlying random variables, one region in uy plane will give you more than one regions in xy plane, and you have to find the area of all those regions in xy plane and find the probability of all these events and combine them together to relate it to the probability of u and v over that rectangular region. This is shown in this slide. So if this is uv plane, u-axis, v-axis, this is the rectangular region bounded by point P1, P2, P3 and P4, and if the mappings G and H are many to one, then the inverse mapping will give you more than one parallelogram shaped regions on X, Y plane, and you have to combine the areas of all these parallelograms, multiply them with the joint PDF of X and Y under these areas, combine them together, and then equate that to the probability of this event in UV plane. And when you combine all these things together, you will have an expression for joint PDF of U and V in terms of joint PDF of X and Y. But this expression will have many components, and each component will represent the inverse mapping of this rectangular region on the XY plane, the parallelogram, and the Jacobian which is applicable to that inverse mapping. Using this technique, you can solve for joint PDF of U and V in terms of joint PDF of X and Y when they are related to each other by mappings G and H which are not invertible. I have applied this principle to the example we were discussing in previous lectures, the example of two televisions, their service times being represented by underlying random variables X and Y, and then some derived random variables like sum of service times, difference of service times, and ratio of service times. This time I have defined U, which is the first mapping to be absolute value of y minus x or x minus y. With this absolute value, this mapping becomes 2 to 1, because if the difference y minus x is 2 or minus 2, you get the same value of u to be 2. So this mapping is 2 to 1. The other mapping is same, v is equal to y plus x. I have used these two mappings, and there will be two inverse solutions, and there will be two components in the joint PDF of u and v, which will be expressed in terms of joint PDF of x and y, which is known, and there will be two Jacobians evaluated at two inversely mapped parallelogram regions. You can see this work done in your handouts and in the slide that you can see now, and this clearly shows that this principle can be applied to those mappings which are many to one, and the end result of this procedure is that you get a joint PDF of u and v for this mapping which is not invertible, and this joint PDF of u and v makes sense because it combines all the aspects of the problem that we are trying to analyze. Today we have completed our treatment of transformation of random variables. We reviewed the old case of transformation of scalar valued random variable to a new scalar valued random variable, and analyzed this through a direct approach of finding the PDF of derived random variable directly from PDF of the underlying random variable. And we extended the discussion to those mappings which were not invertible, and by building this solid base, we applied this principle to the case of a pair of derived random variables defined over a pair of underlying random variables, and we concluded this discussion of transformation of random variable by solving a problem with mappings which were not invertible. From next lecture onward, we'll deal with more advanced topics of probability theory like vector valued random variables, correlation matrices, covariance matrices, and other topics. Till then, I wish you the best. Thank you. Khuda Hafiz.